So this formulation right is a little on the abstract side. We need to look at it, some concrete examples which I will do in the course of today's class. I went back and looked at these examples, and it's a good point to bring them in actually. So so the the general n is a little complicated to look at. So let's look at the simplest case, right, which is what, n equal to 2, right. For a useful partition of omega, you need at least 2 events, A1 and A2, right. So let me just start off here and then continue on. The simplest case, right. So that means you have only A1 and A2, right. Actually it's a very important case also, as we will see, right. So here we have A1, A2 with where such that A2 is the complement of A1 actually, right, because you want them to be disjoint or mutually exclusive and add up to omega. So obviously A2 must be the complement of A1. So what is probability of B now? Any event B will be P of B given A, PA plus P of A given B given A complement, P of A complement. This is a very commonly used formula which I am sure you have seen before, right. Let's see how far we can go with this, right. And of course, right, you can talk of the posterior probabilities will right, in terms of both A given B as well as A complement given B, right, both of them will be the posterior probabilities in this particular case, right. So let me, okay, I defined A1 and A2, so let me write A1 here with the proviso of course that A2 is A1 complement, right. So you don't have to write A2 if you don't want to, okay. Okay, so the most common manifestation of this situation happens where, right, this not, I wouldn't say most common, the simplest manifestation, right. Supposing you have a system in which can be in one of two states, right, as we will call them S0 and S1. So the simplest okay, I'll call it example. Some system in one of two states, not just in two states, right. So I will make sure I write this one of two states. Okay, with prior probabilities P of S0 and P of S1, right. And then you make an observation which is one of two possibilities, right. I just write it as R0 or R1. Actually this is also an OR, right. It's either in S0 or the system is either in S0 or S1. So in a given run or trial of the experiment, right, the system takes one of the two states S0 or S1, right, and then you make an observation, right, which is R0 or R1. So it's essentially your omega, the sample space is what, just has 4 points, right. This experiment is not complete, right, until and unless you make an observation. So S0, S1 by itself does not make up the sample space, right. So the sample space consists of one of these possible states and one of the observations. So therefore obviously it is S0 R0, S0 R1, S1 R0 and S1 R1. So you have 4 possibilities for omega. Now rather than writing this sample space like this, it's more intuitive to write it in the form of, right, the state on the left and the observation on the right. As we will see, that's very intuitive to do it that way, or you represent it like this, right, S0, S1, R0 and R1. So here on the right you have you put down what the observation is, and on the left you have the state, which most cases is hidden, right? You don't know what state the system is in, right? Then you have these connections. What are these connections? These are all the possibilities that you can have. You can have the system in S0 and the observation being R1 and etc. etc. All 4 connections are right. All 4 these 4 points are represented by connections, right? So where does this situation, for example, affect communication engineers a lot, right? It's the most basic digital communication system there is, right? S0, S1 is the hidden bit that is to be transmitted, right? And R0 and R1, let's say you have a fixed system is given, right, which spits out again a single bit as observation, right? R0 or R1, okay? And let's say that you're at this point in the lectures, we will assume that if you receive or see R0, you're going to say S0, okay. Let's say you make you've already decided that if you see R0, you're going to say that S0 is a hidden state. That means actually if you get R0, S0 was sent, and so on. And for R1, let's say you say that S1 is sent. So that's one possible way in which this thing happens. Another very different setting but the same mathematics is when what? S0 and S1 represent 2 medical states, right, of an individual drawn at random from a population, sick or not sick, right, or has a disease, doesn't have a disease. And what is R0 and R1 for that? Exactly, you run a test, right, which can come up either positive or negative, and can come up positive also for an individual who is healthy otherwise, right. So that's sometimes called a false positive, right. So, and there is umpteen other applications of this particular model, right. So we will spend some time on it to understand exactly how the calculations go, right. So what are the prior probabilities, right? The prior probabilities are clearly P of S0 and P of S1, which have to add up to 1. Okay, let me write it as. That's exactly the counterpart here, right? If I just have a two-way partition. So it turns out that omega is partitioned in 2 ways by S0 and S1, right? Exactly. Okay. So then you have, right, to complete the probabilistic description, you need the so-called transition probabilities, right? If the state is in S0, right, what is the probability, given that the state is in S0, what is the probability that you are going to make observation R1 or R0 or R1. Now the reason for my choosing this notation 0 1 0 1 is again motivated from digital communication or right, binary communication, if you will, not just more general digital but binary, right. You are sending ones and zeros, you are receiving ones and zeros, that is why I am writing it as indexing it 1 and 0, right. Okay. So so-called transition probabilities, right, which are what they are in the context of communications, right. This will be a collection of 4 of them, which I am going to write like this, right, I given Sj, where I can assume 0 or 1 and j can also assume 0 or 1. Remember, this I and j, you should use 2 different letters here because they can be independently chosen to be 0 or 1 or separately chosen to be 0 or 1, right. So here what are the rules that the transition probabilities have to follow, right. So given S0, you must have, in fact we said this, did we maybe I didn't make this point in last class, but let me make it now, right. So given S0 you can get only R0 or R1, so therefore probability of, let me expand it out and write it so you have R0 given S0 plus P of R1 given S0, this must be 1, and also the other one, the equivalent statement with R1, sorry, not R1, S1, R0 given S1 plus P of R1 given S1, this also must be 1, So this collection of probabilities is the input to, right, to analysis. So you assume that, right, how many parameters have I introduced here? I have introduced 6 parameters, right? The 2 prior probabilities and the 4 transition probabilities, right? Actually, they are not independently 6 of them. There is only, right, independently only 3 of them, right? If you know P of S0, you know P of S1, so obviously you don't count them as two independent parameters. Similarly, so therefore essentially we have, let's say, this, and then for symmetry's sake we can pick P of R0 given S0 and R1 given S1 or something, right, as our 3 starting numbers, right. So how we get these numbers, that's a different issue. As I said, that's a complicated situation, right, and needs a lot of statistical right, observation and testing and so on before you can say, especially in the case of sickness and diagnosis and all that. It's not at all a trivial, right, thing to do. Okay, but we are not going to concern ourselves with how we get these numbers again, right. So we get some numbers, right, which are which are internally consistent. In that, definitely, right, we require this and I mean these 3 equations to hold, right. So what can you now say about, for example, right, what would be this B? This B would be, let's say, the event that R0 is observed, right. So what would be the total probability of B here? It would be, so probability that R0 is observed, remember I said R0 is an observation. So this is an event, the observation of R0. So obviously this would be, using total probability, what would it be? You condition on S0 and S1, right? R0 given S0, P of S0 plus P of R0 given S1, P of S1. And if you write a similar equation for P of R1, right, you would find that R0 and R1 also, the probabilities of observing them will add up to 1. It should be very clear, right. P of R1 observed is P of R1 given S0, P of S0 plus P of R1 given S1, P of S1. Now please add up these two and see for yourselves that they will have to add up to 1 because of these conditions we have put down earlier, right. Okay. Now what would be the posterior probabilities, which I am not going to, I think, exhaustively write down. You can write them down yourself, right. Given that you observe R0, what is the probability that S0 was the actual hidden state? That is P of S0 given R0. When obviously that can be written with, with all the stuff that we have already said. It is not a big deal, right. Remember that, right, this joint probability is what you should use in the numerator, not any conditional probability by itself, right. You can of course express this joint probability as P of B given AI times P of AI. Equivalently here, this joint probability that S0 was actually the hidden state and R1 was observed. So that is a joint probability, it is not a conditional probability, right. So the wording is very important, right. Let me just maybe write one of them, P of, let's say, S0 given R0. I am not going to write the expression, this is the probability that system is in S0 given that R0 is observed, given that vertical bar is the conditioning statement, right. And again by definition or whatever, base rule, whatever you want to call it, this is a probability that system is in S0 and R0 is observed divided by what? The probability that R0 is observed. So note the difference between this vertical line and this and, right. So that would clearly be the, right, this joint probability is the probability of this point, and always, right, this is going to be smaller than this, right. So let us use this simple formulation to figure out, right, for example, the probability of error, right, assuming that, right, if you see R naught, you are going to decide that S naught was the hidden state, right. Let us say we have a decision rule like that. We will revisit this decision making business maybe a little later, but we will revisit it later, but for now we will assume that the decision rule is fixed, right, that if you see R naught, you are going to assume S naught. If you see R1, you are going to assume S1. Let us assume, let us go with that decision rule, right, and see where it takes us, right. So assume right, then you are interested in, right, the making a correct decision, right, the probability of correct decision for this particular decision rule. Now this CD correct decision, I am going to write even later on abbreviate it using CD, right. So again we will use conditional probability to write out this probability of correct decision, right. You can condition on S naught or S1. So this is an event. When do you get a correct decision? Supposing it actually was an if S naught was n, actually you saw R naught, you made a correct decision. Supposing the system was in S naught and you saw R1, then you made a wrong decision. So what is the probability of correct decision? So making a correct decision is obviously also an event. So how do you write this out? So this is exactly the probability of getting this and getting this. So in terms of S naught, R naught, so I will just write to abbreviate this, right, I will just say R naught and S naught, which is the same as R naught, S naught, R naught, or R1 and S1, that is this point. So clearly this can be written in terms of conditional probability. So these two again are obviously mutually exclusive, right, so therefore this is the probability of R naught S naught plus the probability of R1 S1. So this is the probability of R naught given S naught, probability of S naught plus probability of R1 given S1 times P of S1, right. So for the fixed system, this is the probability of correct decision. Alternatively, you can also look at the probability of error, and you can clearly check it out for yourselves that probability of error must be 1 minus probability of correct decision, because there is no other third possibility, either you are right or you are wrong, right. Okay. So let me not give any numbers at this point. I just want, we will be coming back to this example later on, so I just keep this around, right. So of course in our goal in designing these communication systems is to make them work reliably. So nobody would this is a very basic level of the discussion where you are given the whole thing, right, you are just making measurements out of it, right, you are even told the decision rule. So the next thing would be, is it in fact the best thing to do? That is, if you see R naught, should you just close your eyes and always decide S naught? Not necessary, right, you could decide the other way also. So when does it make sense to decide a different way? So that is what we will look at slightly later, right. But for now I think I just wanted to introduce this concept, right, of how the conditional probability comes into this as an analysis tool, right. So